All right, we're going to look at section 10.3, parametric equations in calculus. In other words, all the things we did in parametric equations in 10.2, how we're going to apply them here. So the first thing we want to be able to find the slope of a tangent line to a curve. That sounds familiar. We've done that quite a bit already, but now given a set of parametric equations. Next, we want to find arc length of a curve given by a set of parametric equations. And finally, area of the surface of revolution in parametric form. All those are familiar concepts. We're just going to apply them now to parametric equations. So take a look at this first one. We've seen this example before, and we're launching something at an angle that was a 45-degree angle, and we came up with these two parametric equations. So initially we launched it at 45 degrees, but you realize that gravity is going to take effect and say, how can you find the angle representing the object's direction at some other time t? Well, the following theorem answers this question by giving the formula for the slope of the tangent line as a function of t. In other words, we're going to be able to find that slope, and I don't think I can zoom in on this, but you can see that angle would be the difference between the path that it's actually on and the horizontal. Okay, so that's kind of what we're looking at. The slope of that tangent line there will help us out. So guess what this is? It's our derivative dy dx, which now has a different form than what we've seen before. It's given dy dt over dx dt. So these are, we're looking at with respect to t now instead of with respect to x. We've seen this before as part of the chain rule. So here I've got dy dt over dx dt. So at any given point, as long as dx dt is not equal to 0. Let's go ahead and find that for this first one. Okay, so x is equal to sine t, y is equal to cosine t. Those are my parametric equations. Let's go ahead and find dy dx. All right. So just a minute, let's go back. Dy dx is equal to the y's rise to the top again, dy dt over dx dt. So dy dt over dx dt. And that is some really nice handwriting. Okay. And the derivative of y with respect to t is, thank you, negative sine t. And over dx dt, the derivative of sine t with respect to t is cosine t. Which then we can write, we know sine over cosine is tangent, so this is the opposite of tangent. T, where t of course is not equal to pi over 2, 3 pi over 2, etc., etc. Okay, so we have some limitations, some restrictions on that derivative. How about down below? I want you to try that. Notice this is the square root of 2 times t, not the square root of 2t. So make sure you understand that when you're taking its derivative. Go ahead and try this one, see how it looks. I think you won't find it too challenging. All right. Dy dx is a function of t. You can use theorem 10.7 repeatedly to find higher order derivatives. So here's the second derivative, and here's the third derivative. And notice they get a little messy. Here we've got the derivative with respect to x of the derivative. And we write that then as the derivative with respect to t of dy dx over dx dt. Keep this in mind. We're going to use this one a whole lot more than we're probably going to use the third derivative, because we want to look for things like concavity and those types of things. But you'll notice it's the derivative with respect to t of the derivative of the first derivative, basically. The bottom simply stays dx dt. You only do that once. Okay, so let's try that out on this one below. See if we can click that. Here we go. So determine the time t intervals on which the following curve is concave downward or concave upward. So of course we're looking for the second derivative, but first let's find the first derivative, which is equal to, and that's dy dt, which is on top, so that's 2t plus 3t squared is the derivative of y with respect to t over dx dt, which is simply 2t. And if you want to, you can simplify this. We might want to do that. You can see a t would factor out of everything, and we'd be left with 2 plus 3t over 2. Okay? Now if I go back here and say the second derivative is the derivative of the first one with respect to x, or simply the derivative with respect to t of dy dx, so that's what's going to go on top. So we're going to try that. Alright, so it's the derivative of this with respect to t. Now I'm going to rewrite that one more time. I'm going to write that as 1 plus 3 halves t, because that looks easy to me. Because what's the derivative of this with respect to t? Well, simply 3 halves. That's supposed to be a 3. Over dx dt, and did we do dx dt? That's right here. That's just 2t. So that looks a little bit ugly. I think we can probably clean that up a little bit. And we'd get, first one I'd leave alone, the second one I'd flip. We'd get 3 halves times 1 over 2t, which is equal to 3 over 4t. Or 3/4 times t to the negative first. Alright, when is this concave up and when is it concave down? So it's concave up. Of course, when t is greater than 0. And concave down when t is less than 0. Alright, so far so good. Let's move along. Now we're going to take a look at this prolate cycloid in just a sec. Alright, this example is fairly complex. Let's take a peek. We've got a prolate cycloid given by x equals 2t minus pi sine t and y equals 2 minus pi cosine t. It crosses itself at the point 0, 2, and you can see that happening. It goes around, comes back through here, the point 0, 2 on the rectangular piece, as shown in this figure. Find the equations of both tangent lines at this point. Okay, so what we're going to try to do is come up with that based on what I know about this. The equation of the tangent line, we're going to need to know its slope. Its slope is its derivative, and so we'll do that right away. We'll take, we don't need that, that's okay, dy dx is equal to dx dt. Just hold on a minute. Okay, sorry for the technical difficulty. Here we've got dy dx, of course, is dy dt over dx dt. Which is equal to, alright, dy dt, it's right here, not too bad. That's of course 0. This is simply pi sine t over dx dt, which is a little more complicated but not much. The derivative here is 2, and then minus pi cosine t. So that's its derivative. And what we need to figure out then next is, to come up with the equation, I need to know at what point. Well, we know the point is 0, 2, but that's in terms of x and y, not in terms of t. So let's find that t value. So this would in essence be step 1. Let's take a look at step 2, where we're going to say, well, x is equal to 0, so I'm going to get 0 equals 2t minus pi sine t. That looks fairly complex. If we try to solve that, I can add this. I get pi sine t is equal to 2t. Sorry for the bad writing. Right, and then solving that. Ooh, it looks kind of ugly, doesn't it? We might have to stop there for a minute, because that doesn't look so good. So let's go ahead and try the other one. Let's put 2 in for y. So I get 2 is equal to 2 minus pi cosine t. And if we subtract 2, we see that 0 is equal to pi cosine t. So really what I'm looking for is when is the cosine function equal to 0. So cosine of t equals 0. When t is equal to. And the obvious one, hopefully obvious, is at pi over 2. But there are others, and so let's consider where else. You know, I look at this, I say, well, I'm coming from the left and I'm going to the right. I'm also going to consider t equals negative pi over 2. So that's the end of step 2. So now we're saying that the derivative at these 2 points. So let's go ahead and step 3 says, let's find that derivative. So dy dt, excuse me, dy dx at pi over 2 is equal to, let's substitute that in. Sine of pi over 2 is 1, cosine is 0, it looks like pi over 2. And the derivative at negative pi over 2. Sine of negative pi over 2 is negative 1. This is still 0, so that becomes negative pi over 2. Right. Step 4 then is to substitute these in, because I know a point, I know the slope, that's right here, and so I just simply put those in. Y minus 2 is equal to pi over 2 times x minus 0, which is simply x, or, so that's one of the equations, y is equal to, excuse me, y minus 2 is equal to negative pi over 2 times x. So, and I can solve those for y. That's my final. All right, we'll pick up the next part of the lesson in step 2.